Started. And I'm first going to describe Dr. Huang's portion. He's going to talking about mobile EEGs for real-world BCI applications. So most of you are hopefully doing some kind of EEG. We're not going to be describing what EEG is. We leave you to look at up on Wikipedia or through our other webinars. But most of you are using possibly some research-grade EEG systems that typically have an amplifier box on the table and some cables going to some kind of headband positioning the electrodes in place. On the consumer side, people want things to be more wearable, more aesthetically pleasing, more wireless, and you might have something that looks quite pretty but may not have the necessary functionality to get meaningful or useful EEG signals. So we are striving to be somewhere that can reach both of those. Our goal is to provide sufficient channel and head coverage to be able to do some meaningful EEG data analysis. It's important to have signal quality that's as good, if not better, than traditional systems. And our systems need to also be immune or quite resistant to interference from environmental and motion artifacts that can happen in real-world environments. Also, in the real world, we cannot be tethered to our computers, so the systems need to be wireless. So these are the three principles that we're going to be discussing to found as the foundation for a mobile or wearable EEG system, research-grade EEG system. So this is Neuracle's Nucin W. This is one of their flagship products. It can sample up to 64 channels of high-quality EEG wirelessly at up to 16 kilohertz per channel. That's a lot faster than most people need to sample EEG, unless you're trying to do brainstem evoked potentials, but that's a really fast and powerful system. It's quite lightweight, it's small, it's about the size of a credit card, a stack of probably 25 credit cards or so, and it's quite robust to ambulatory and motion artifacts, as I'll show you in a second. So this is the system, what it looks like. There's a wired hub, there's a trigger receiver, all the system gets connected pretty quickly. There's a magnet on the back of it that allows it to snap onto the cap. This is what the cap looks like when it's fully donned. And now we're going to show you the donning process. They do have medical grade software, and this is what the process of equipping the cap looks like. So you have some gel. Sorry. The gel is loaded into the syringe, and a blunt end needle is placed, so that's not going to hurt the person. It's not going to poke them. You load the gel into each of the electrode holes, and you can use the blunt end needle to work the gel through the hair to move the hair out of the way. You can hold the plastic holders and shake them to move the gel through the hair. And you can also use the blunt end of the needle to do a little bit of scalp abrasion by rotating it against the scalp. The process is not painful. It's quite efficient. It can go pretty quickly, and all throughout you can check the impedances in real time and see how your impedances are looking, with the goal of reaching below 50 kiloohms, ideally below 20 kiloohms. We have had no problems reaching below 5 kiloohms on most electrodes. As you can see over here, once the electrode impedances are set, you can start inspecting signal quality. So this person is blinking. You can see the blink artifacts in the top rows. So each black row, the data stream is a channel of EEG data. And then the top ones are frontal, the back ones are parietal. So this person just closed their eyes. You could have seen, you saw the alpha activity there. Now they are clenching their jaws. So you can see a large EMG artifact, and you can see it recovers quite quickly after the EMG artifact. These are some more blinks. And now the person is going to shake their head. And you can see when they shake their head, there are some EOG artifacts. That's because the eyes are rotating in the socket or he's blinking. But there isn't that much artifact on the rest of the EEG channel. So the headset isn't shaking and wobbling just due to the movement of the head. Next, he's going to walk around. So you're going to see resistance to movement, casual movement. So he's walking, and you can see his blink still. but you can see it's quite immune to his walking artifacts. So there isn't any artifact that's happening when he's just walking beyond his blinking. Now he's going to jump. When he jumps, you see a very rapid transient, and that makes sense. So there's some limits to this, but it stabilizes and recovers quite quickly. Of course, if you were to jog, you get also some motion artifacts, but they recover quite quickly when he's not jogging. So we can do some movement, we can do some casual movement, but there are some limitations to the system, of course, which then leads you to using potential artifact removal algorithms. But what the data you were seeing right now did not have any artifact removal. This was from 1 to 40 hertz filters applied. So here Neuracle did a quantitative analysis of classification of BCI spelling, or in this case, numbering, while the person was jogging at a slow speed on a treadmill, and they looked at the response to classification accuracies. So they were comparing it to state-of-the-art EEG system. In this case, this was Neuroscan. That was the amplifiers were in the backpack, and it was tethered to the computer. You can see that when they were standing, the classification accuracies were quite comparable. Sorry. When they're walking, again, the classification accuracies are quite comparable between the two. It is only once they start running that you see a decrease in the classification accuracy of both systems, but a lot more in the Neuroscan. Here is those results plotted. So this is the classification time, and you can see that for the walking and standing still, the classification accuracy of both systems is about the same. The longer you collect data, the better your classification is. Once you start running, both systems' classification accuracy dropped, with Neuroscan dropping, sorry about that, significantly worse than the Nucent system. So this was a demonstration of the robustness to motion artifacts. So how is that accomplished in the system? There are a number of things. First, the amplifier is inside the case right here, which is mounted on the headset, and there are very short distances for the cables. So the cables are not going to have much distance to pick up motion artifacts. They're not moving around, which is often a cause of picking up motion artifacts. Two, the system is wireless, and therefore it's going to be insulated from the mains. So it is essentially, there isn't a cable, electrical cable that's carrying noise onto it. I'll illustrate that in a second. Here we go. So here's the power spectrum of data collected from the Neuroscan system. In this case, they're pushing it into an extremely noisy environment. This is a NICU incubator. The data is, you can see the spikes over here of the 50 hertz mains frequency in China. And you can see additional spurious spikes, as well as a very high noise floor for the EEG data. It's so high that it's masking the 10 hertz alpha activity. And then on this side over here, and I think this is scale has been shrunk on this axis, but it wasn't correctly shrunk on this axis. But you can see that the noise here is on the order of up to 20 microvolts. Whereas here it's going up to 40. So this system is much more robust to this environmental artifacts, and you don't see any pickup of the mains frequencies or their harmonics. All right. So we mentioned that the system is wireless. It has a 5 gigahertz Wi-Fi system inside it. So this allows the extremely fast data rates, but it also is quite immune to data loss and signal interference from other Wi-Fi or wireless systems. The system also allows really high accuracy synchronization across multiple devices, which enables hyperscanning on up to 8 devices. So it's 8 people together in the same room. Furthermore, they can also, using their trigger hub, they can send trigger events that can be synchronized across all these subjects, enabling high accuracy ERP signals. And I'll show you some examples of that in a second. All right, so I'm going to show you an example of an ERP task. In this case, there's going to be images of faces, houses, scrambled, and some targets that are going to be shown. So this is a RSVP paradigm. Subject is asked to fixate on the plus, and you can see the images are going to flash rather quickly. At the end, we can take it to EEG lab and do the analysis, and I'm going to fast forward through that. So this is what the raw data looks like. So in this case, you can see that most of the channels are clustered quite nicely. You can see this purple one. This is the ECG channel, which has a different response curve, power spectral density. And you also have this channel over here in blue, which is a channel that was shorted where the gel connected the electrode to the reference. So this is what the short would look like. Next, when we zoom in a little bit, we can see that here is the 50 hertz mains. It's just very, very small. And when we start doing our ICA, we can see there are a number of components that show up. You get so this is one of the really useful things about having a high density array. You have high spatial resolution EEG, which allows you to look at vectors and a lot of different components. So here, for example, you can isolate a muscle artifact. Here's another small muscle artifact that may not have been separated with lower resolution systems. All right. Here is, oops, sorry. So when we go further to looking at evoked potentials, here's a summary of at P8 of the 3 responses to faces, houses, or scrambled images, and you can see a different amplitude of the responses, allowing you to distinguish what type of object they were looking at. And when we look at the trials across time, so now on the y-axis you have each individual trial. On the x-axis you have time. This is the event of showing the picture. This is the shape of the average ERP, and you can see very nice low noise background, very clean high signal to noise ratio ERP, and a very sharp delimitation of the onset of the ERP. So this is, you can clearly see from this that we can do single trial classifications quite easily. Next, I'm going to show you an example of a BCI task, which you may be very familiar with. This is the SSVEP speller. In this case, it flickers the checkerboard display on top of the keyboard, and the user is able to spell by attending to the various letters that they're interested in spelling. Here, he just made a mistake. He uses the back arrow, and he's able to correct. So it's as they attend to each particular letter, the flickering frequency of that letter is unique, and the algorithm can detect that and spell out, guess the character that they're aiming to spell. So that same principle can be used to do a lot more things in the real world. So here are some examples where we're using a similar SSVEP paradigm to control a robotic arm. In this case, the display on the monitor is showing 4 different targets. And you're able to, by attending different ones of these targets, send commands to the robot arm to ask it to do different tasks. Similarly, you can also wear a HoloLens device in which, where in the augmented display, you have a screen that has the 4 targets, and you can send the commands to the robotic arm by fixating or attending to the various targets. And here are the classification accuracies, and you can see that in both cases, they're doing better than 90% classification accuracy with an ITR, so information transfer rate, of 17 bits per minute or 14 bits per minute. So this can be quite fast. On the speller, they can do quite faster than that as well. So a few other examples of real-world BCI, or at least research-grade BCI. In this case, they had on the left side, they had an expertise assessment. So these subjects were invited to play a multiplayer game online, and you could look at the EEG signatures. And by looking at the synchronized EEG signatures, they could determine professional from amateur players. So that's a nice case of looking in real time at hyperscanning studies to assess expertise. On the right side, they were using an ERP-based approach to determine the type of human cooperation. So in this particular task, the two participants would have to collaborate on a task, and they could either help each other or not help each other, and they could look at the ERP responses of each of the individuals and determine what role they were playing, whether they were playing collaboratively or counter-collaboratively. Again, an example of the utility of having highly synchronized data to be able to do ERPs and across subjects. Sorry. I'm going to skip over that one. So in this case, we're doing a control of a drone on the left side in the real world, and in a shopping mall while being videotaped, and the person is able to use some very simple commands to control the drone while the person is talking to him even and interacting with him. And on the right side is a demonstration of using EEG to control the speed of the exoskeleton. So in this case, the user is controlling the exoskeleton by moving his legs. However, the speed of response, the reactivity of the exoskeleton is controlled via the augmented display, augmented reality display under the helmet. All right, so those were some, sorry about that. Those were some illustrations of real world BCI being applied in the real world. So what we had here, we had a system that had 64 channels, so a very good channel coverage on the head. We had a very good signal quality that was immune to motion artifacts as well as to artifacts that could have been produced by the robotic arms, by the exoskeleton, by the drone, by other environmental factors in the mall. And the data was all transmitted wirelessly, so the person wasn't tethered. We had good enough signal quality that we could do meaningful and useful BCI applications. So I hope that was a useful demonstration of those capabilities. And next, I'm going to move into the wearable sensing's world, which is that of dry electrodes. So if you don't know us already, if you don't know us by now, Wearable Sensing has brought to market technology developed by a company called Quasar. So Quasar had developed a breakthrough dry electrode EEG technology, and Wearable Sensing has been bringing those sensors and headsets to you as researchers to develop real-world applications of brain-computer interfaces. So we just showed you a very nice wet electrode system with great capabilities. One of the limitations of wet electrodes is this need for skin abrasion and the use of conductive gels. You typically need to abrade the skin to get rid of layers of dead cells and oils and fats and tissues so you can get a good contact impedances between the electrodes and the skin. During the process of abrasion, you create little micro cracks on the skin, which when you load the gel can go through those, create a nice wet-to-wet contact, and then a wet-to-metal electrode contact, which has low impedance. Low impedance means that the EEG signals that are very small can cross this bridge on the gel and go to the electrodes and reach the amplifiers without too much interference of noise. If you don't do a good job, or when the gel dries up, you can start getting artifacts. Also, the cables can, if they're not active or shielded, can pick up motion or electrical artifacts from the environment. Most systems are not as small and compact as the system that I showed you, so they're typically not portable and not ambulatory, and they're usually not seen as a technology designed for real-world or virtual world applications. So the system I showed you just a little bit before was quite unique, and for us, our mission was to overcome this hurdle of wet electrodes by using dry electrodes. So in this slide, I'm going to describe this dry electrode technology. While I'm doing that, on the bottom right over here, I'm going to play a video where Cameron is self-donning the headset on his own. This video takes about 2 minutes, so you will see the, if it's playing, there we go. You'll see the donning process in what it looks like in real world. Cameron, is it freezing for you?
Yeah, it's a little glitchy, but I think it was like that before, so I think it's okay.
Okay. So I have all right. Let's see if it's less glitchy. All right. So we had a mandate. Quasar had a mandate to develop dry electrodes. This mandate came from DARPA initially, and then later from the Army, Air Force, Department of Defense, NIH, NSF, all had some funding that went towards developing these dry electrodes. So Quasar took its capacitive electrodes, added ultra-high impedance amplifiers to them, created a hybrid capacitive and resistive dry electrodes. We added silver chloride pins to these electrodes to allow them to go through the hair, and we developed a very functional dry electrode. The sponsors were keen on having signal quality that was not compromised. There would be no compromise on signal quality. So we did quite a number of experiments to validate that the signal quality we were getting from the hybrid dry electrodes was comparable to that obtained from the wet systems. So here you can see traces of alpha activity recorded simultaneously with dry and wet electrodes side by side. And you can see that we get better than 90% correlations, very good matching on both the large components and the small components of the EEG signals and frequencies. And then the sponsor said, this is great. However, we want to make sure that you don't have artifacts. We hear that EEG is very prone to electromagnetic and motion artifacts, and dry electrodes even more so. And that was true. So we developed quite a number of technologies to mitigate that. On this side over here, you're seeing a spring that allows us to mitigate the effect of the movement. So if you imagine the fingers holding the electrode or a headset, if the headset moves, the inner electrode, which is a sensing element, stays put and senses the signals from the head. The inner electrode is the sensing element. The amplifier is immediately behind it, and behind that amplifier is that spring. Everything else you're seeing over here is a Faraday cage. So a Faraday cage is an electromagnetic shield that is protecting the electrodes and the amplifiers from electromagnetic interference that comes from the environment. So this means that the only place signal can come in is from the underside, going through the electrodes into the amplifier, where it gets amplified before going out and getting digitized in the headset. So this way we can protect ourselves from electromagnetic noise. This way we can protect ourselves from motion artifacts. And in a second, I will show you our robustness to motion artifacts. Once we had these sensors that worked so well, we needed to develop a system that could be easy to put on, comfortable to wear all day, and easy to put off, to remove by oneself. So you saw this donning took a little bit over 2 minutes. It was 2 minutes and 10 seconds when he was done. And you'll have to trust me right now that it's comfortable. This is Cameron, his best smile. No, he's got a great smile, and it's quite comfortable. So if you'd like to trial the system, please reach out to Cameron, and he'll be happy to arrange a demonstration for you guys or the trial. Lastly, of course, the system has to be ambulatory, so it had to be wireless, and therefore all the electronics and batteries are embedded inside the headset. All right, so let's take a look at what the signal quality looks like. So this is, first we check the impedances. The impedances are below 1 megohm, which is quite large for a wet electrode, but it is acceptable range for us, given the precautions I mentioned, the ultra-high impedance amplifiers, the shielding, the Faraday cage. So now we're looking at the EEG signals. Here are some blink artifacts. So we have less channels than what we saw in the nuisance system. But we can see in the top as a frontal electrodes, on the bottom are the occipital and parietal. Here are some EMGs, so he's biting his teeth, and you can see the large high frequency signals, and then it recovers quite quickly thereafter. Now he closes his eyes, and you will see the alpha activity bursts, mostly in the parietal area and the occipital areas. So now he opens his eyes. Next, what he's going to do is he's going to tap his foot. So you can't see it on the screen, but he's tapping his foot. So what is happening here is this red channel is showing the common mode signals on his body. This is the artifact carried from tapping his foot against the carpet, generating triboelectric discharges that get carried on the body. And those can be picked up by the system. We can measure them. And you notice, however, that they weren't present in the EEG. Here, he removed the low-pass filter, so you can see an increase in 60 hertz. He's holding a power cable right now outside of the screen view. And so you to accentuate the amount of pickup, and again, nothing in the EEG channels. So we can see that some pickup is happening, but it's not affecting the EEG channels. Now he's going to get up and walk, and every time his foot strikes the floor, you'll see a discharge of triboelectric signals. So those are his footsteps, and you can see the EEG is completely unaffected. Now, please keep in mind, there is no artifact removal being done here. This is just good EEG design as we just described. The only filters are the 1 to 50 hertz filters. And now the camera is doing his beautiful dance, and you can still see that the signal is quite immune. When he jumps, of course, we hit the limits of the system. You get a brief artifact, but it quickly recovers. And here he was running a little bit in place. You saw some artifacts, but then as soon as he stops running and starts walking again, it's quite clean, quite artifact-free. So that was a demonstration of the signal quality of the system and showing you guys how fast and easy it is to put on and the signal quality you're able to get out of it. So next we will go to show you some data quantitatively, or at least some sample data traces. So this is again side-by-side wet and dry recordings. This is eyes open activity. This is alpha activity during eyes closed. Here are some blinks. This is measured at FZ, I believe, which is why the blinks are smaller. Here's an artery evoke potential, which we'll go over in a little bit, but to show you that, again, even the stimulus happens at time 0, both the wet and the dry system have the same shape and amplitude of the evoke potential, and even the pre-stimulus signal has the same shape and amplitude. Here is a steady state visual evoke potential with flickering at 10 hertz, and we can see the 10 hertz peak and the 20 hertz harmonic in both systems. This is a power spectral density plot. All right, here I'm going to show you an example of an artery evoke potential. So in this case, we play tones like this. And we're able to look at the evoked responses. First, here is the spatial map of the 5 hertz band, of the 10 hertz band, and the 22 hertz band. So you can see, you can get some very gross mapping, topological mapping by looking at with just 19 electrodes. Of course, you can do BESA or S-Loretta and improve and do source localization with 19 electrodes, although most people might prefer to do that with more channels, 32 or 64 at least. All right, so here are the evoked response, audit revoked potentials. Again, the time 0 is when the tone happened. This is the N100 and the P200 response, and here they are plotted in 3D on the topologically. And here is the trial by trial response. So you can see at time 0, and you can see the very good synchronization of each trial's response. Again, this is a wireless trigger that we have as well. And you can see the good contrast between the ERP and the pre-stimulus signal, allowing us to also do single trial classifications. When we go to do ICA, you'll notice that we have far fewer ICA components than we had with 64 channels. In this case, we have 19 instead of 64. So you get less ability to remove and eliminate noise artifacts than you did with the 64 channel system. Here is Neuracle's BCI software. So this is the, again, speller task. I'm going to show that task here, so this video plays. So again, the task here is to attend to the letter of interest, and then the EEG signals are detected and wirelessly transmitted to the computer, where they are processed for different frequencies. And there's a particular algorithm that allows the discrimination of the target letter that was flickering at that specific frequency. Excellent. And you can see that this is quite fast as well. So we have a number of EEG headsets. We have the DSI-24, which has 19 electrodes on the head and inputs for auxiliary channels. We have a DSI-7 with 7 electrodes on the head, DSI-4 that's designed for sleep. It has 4 electrodes on the forehead. We have a flex system that has electrodes that can be positioned anywhere on the head using a membrane to position it in place, a brain net. And we also have some headsets that were designed for virtual reality, but can be used without virtual reality, and those were designed for BCI applications, specifically P300 task or visually evoked potential task. So these are the locations in orange of the electrodes. We have child-sized versions of each of our headsets, and most of them are quite compatible with VR systems or AR systems. We also have a number of multimodal physiological sensors. So beyond EEG, we can record ECG with dry electrodes, EMG, EOG, galvanic skin response, GSR, respiration, temperature. We have 3D accelerometers in most of our headsets, and we have recently integrated an FNIR system around each of the EEG systems, allowing simultaneous EEG and FNIR measurement. We also have incorporated TDCS simulation from Soterix Medical, and we can interface seamlessly with motion tracking from TE Ergo and various number of eye trackers, including those from iTech-DS. So those were our systems. Let's talk about some of the BCI applications for real world. So the first example I show is one that many BCI researchers start with and really is a key driving factor force in BCI research, and that is the ability to use your brain to communicate. So this is a BCI for interface with an alternative augmented communication system. This system is being used at OHSU, and there are a number of other researchers around the world doing similar work. Here, this picture is from the group at OHSU. So what most of these researchers working with locked-in patients who are not able to move any muscles voluntarily or use their speech or vocal cords, so they can use their brain signals and BCI to drive the computers to do spellings, as we just shown you, or to control the computer for other purposes. What is needed for these patients is they need a device that's easy and fast to set up so that caregivers don't have to spend a lot of time setting it up. They need a device that has no gel and that's easy to clean up, because it's critical for them to be, it's hard for them to shower every day. They don't want to have gel in their hair for the rest of the day, which then becomes really hard to clean. It needs to be comfortable for long-term daily use. This is something that they'll need for the rest of their lives on a daily basis. Of course, in order to do meaningful classification, you need high signal quality. You need to have a low jitter trigger with high timing accuracy. The device needs to be wireless so that they're not getting entangled with the wires wrapped all around. And it needs to be robust to electromagnetic interference, as some of them are sitting on wheelchairs. There are a number of other devices in their environments, in their real world, and they cannot be worried about interference from other devices causing spurious classifications. And for the researchers, they also need some kind of real-time application programming interface or an API, so that they can interface with their EEG system, with their BCI software and their AC or whatever they may be trying to control downstream. So this is one example of BCI being used in a real-world environment, though in a context of research, but really research in the home environment of the users. Here's an example of our EEG devices being used in a rehabilitation context. So hopefully many of you have already heard of Neuralutions, which recently cleared the FDA with this device, which is a combination of our headset with a prosthetic robotic exoskeleton. This device is designed to use the brain signals to help guide people during rehabilitation exercises, to help encourage neuroplasticity and encourage the new connections and formations and recovery from stroke. So this device was recently cleared, and we're excited to see the work of Neurolutions to launch in the market. Here's a very different application. In this case, this is an enterprise application. A company called NRI is using our headsets in airports for enhancing airport security. So typically, the security line, you have one X-ray operator for each one of the X-ray machines. And use case where they're able to have X-ray operators using an EEG device, they can show them the pictures from multiple scanners and a rapid visual stimulation paradigm, RSVP paradigm, and they can improve the efficiency of the line. They can now have one operator operating 5 X-ray machines. They use a little bit of artificial intelligence and image processing, but with the EEG, they can get really increased detection accuracy and operational efficiency. So this is a very interesting application of BCI that, again, really needs dry electrodes because these operators are not going to be willing to put gel in their hair to do these recordings. There are, of course, people doing neurofeedback and peak performance training. So neurofeedback is the use of the EEG signals to and train people's networks towards a recovery state. So if a person has ADHD or sleep disorders or anxiety or stress, you can measure the EEG signatures, compare them to a normative database, or apply some different algorithms and give them visual feedback of their brain states, allowing them to gradually over time gain ability to control their EEG signals. And therefore regain some of the functionality. So reduce stress, reduce anxiety. On the peak performance side, it's a similar paradigm, only instead of being rehabilitative, it is augmentative, where you might want to train athletes to improve their focus, their flow. You might train students to improve their memory, their attention span, again, by giving them visual feedback of their EEG signals and helping guide them to reinforce using typical classical Pavlovian conditioning or neuroplasticity principles to strengthen and reinforce the networks by giving positive reinforcement feedback for brain activities that are desired and negative reinforcement for brain patterns that are less desirable. 2 other BCI applications that I'm highlighting here is neuromarketing. So there are a number of people using our devices in neuromarketing space. Here I'm showing an example of Deloitte. So in this case, neuromarketers are interested in knowing the subconscious desires or impressions of advertisement or movies or products on a person, on a user, on a consumer. So they will equip the person with EEG devices and typically also with eye trackers, and they would show them images or videos or take them through a supermarket and observe their brain responses. Various algorithms have been developed or are being explored by different groups to get measures of arousal, to get measures of engagement and memory. Is the person enjoying what they're doing? Valence. Are they excited about it? Are they going to remember it? Are they paying attention to it? These are the kinds of questions they're asking and looking at the subconscious responses, because they find that it's difficult for people to give them real answers, honest answers in real time in an efficient manner. And last but not least, a very beautiful art exhibit was developed by EPFL and some collaborators. It's called Mental Work. There they used BCI with motor imagery. They had museum attendees don headsets and go through a motor imagery training task where they'd learn to control their brain states by either imaginary hand movement or hand movements. And then they would pass them through the museum where they would interface with various machines, such as the one shown over here. Then they would be able to perform their motor imagery tasks and control these machines to move and kind of emulate how the brain could be able to control the machines in the future. So this was a beautiful art exhibit conducted at TPFL in Switzerland. All right, so I shared with you some interesting work by both the groups of using high density systems and some groups using dry electrodes. A question often comes, what system should we use? There is no right answer to that. It really depends on what you're trying to do. There are trade-offs between the two systems. A high density system can be very useful if you need high spatial resolution brain imaging, brain mapping, which our dry electrodes today with 19 electrodes cannot do very well. You can do some source localization, you can do some ICA, but it's not as good as what you can get with the high density system. So conversely, some applications need a fast setup, fast cleanup, a comfortable system. They need to be multimodal. This is places where the dry electrodes shine. So there are trade-offs between the two systems. So if you're not sure what your application needs, please contact Cameron. Let's figure out what the right match for you. And of course, you can get one of each system, and then you don't have to sacrifice. You just do one experiment after the other. All right, so what I would like you to remember from this, we showed you some high signal fidelity wireless systems that are robust to motion and electrical artifacts. We showed you how easy it is to put them on. You'll have to trust us on comfort or take us up and ask to trial our systems. They're fast to set up. Even the wet system is relatively fast to set up compared to when I was a technician. We had to manually position each electrode. They are multimodal, and they're compatible with AR, VR, and the real world environments. So with that, we open it up to your questions, and I'll just conclude by saying that our next webinar will be in July. We are inviting one of our customers to come present their work that they recently published in Journal of Nature, and they basically did some very nice work. They're measuring EEG on patients with autism, and they could, with their artificial intelligence, they could classify stressful states from a non-stressful state with high accuracy. So this will be a research presentation. It won't be focused on the dry electrode aspect, although the dry electrode was quite useful and important in order to be able to measure signals from this autistic population and get reliable and good signal quality from them. With that, I open the floor to your questions.
Awesome. Thank you for the presentation. As Walid mentioned, if you guys have questions, feel free to send them either in the chat or in the Q&A. We do have a few right now, so send them in while you have the opportunity. But we'll go ahead and start off with what are the differences between dry electrodes and conventional amplifiers?
Okay, thank you for the question. So a conventional amplifier typically has input impedances that are much lower than what we do. So they're usually in the mega ohm range, whereas our our amplifiers have inputs in the range of the over 47 giga ohms. So that's quite a lot larger than. So this is sorry. One difference between the amplifiers of a dry system versus a wet system. The other part is the dry electrodes are usually active, meaning the amplifiers are at the electrode tip, and that is quite important in order to amplify the signals immediately at the source before this high impedance signal goes through large cables where they can pick up a lot of environmental artifacts. So by amplifying the source, you turn it into a low impedance signal that can go and get carried through the systems further. Other differences, in our case, we have a Faraday cage around each sensors, and I know that other groups have now also started following suit and doing that, and that's quite critical to protect, again, from environmental artifacts. And the biggest, most obvious difference is the lack of gels, and the lack of irritation and need for rubbing.
Awesome. Next question is, what is the minimum number of electrodes needed to do source localization?
That's an excellent question, and I wish there was a definitive answer. Unfortunately, there is still debate and discussion about that in the research world. Most people, well, there are some people that do source localization with 19 electrodes using methods such as S-Loretta or SW-Loretta or BESA or other approaches. And there are some people who believe that in order to get really meaningful source localization, you need a very high resolution, very high density electrodes to enable you to get meaningful resolution between the spacing. So people will say that you need 32 or 64 channels at least, and agree that 128 is better. When it gets up to 256, there's some debate there about the increased value because the electrodes get so close together that you very often get shunting between electrodes, and that is counterproductive to getting good resolution.
Awesome. Thank you for that. Next question was a compliment. Amazing presentation. I found the AR combined with DSI systems to be really interesting. Besides HoloLens, are there other possible AR/VR headsets compatible with DSI systems? Are there efforts going into making a generalized GUI for BCI combined with AR/VR?
Okay, lots of questions in one. First, thank you very much. We have interfaces specifically at the moment for the HTC Vive, the HTC Vive Pro, and the HTC Vive Pro I. We have an interface with the Oculus Rift and the Oculus Quest. We have customers who have interfaced with other devices, including the HoloLens. There are people using other AR devices that I don't know what brands, but those were the ones I mentioned are the ones where we made specific interfaces that allow the headsets to connect directly to each other. With regards to API or interfacing or how to connect the data between one and the other, there are a number of ways to do that. We have an API that provides the data, raw data, that needs to then be passed on to Unity so you can pull the data from our API and then call it into Unity. There's a company with whom we developed initial VR interfacing, the interfaced headset. That company is called Neuracle. They developed an SDK that not only ported the data, our EEG data, into Unity, but also did some processing initially for data synchronization, for P300 classification, but they also added some additional algorithms for cognitive state assessment recently. So they sell that product that is available. There are some free open source solutions such as Lab Streaming Layer to which you can pass our data, and then there is LSL for Unity or Unity for LSL plugin that allows you to pass the data back and forth into Unity and do interfacing. We have other commercial solutions such as the Captive system that allows you to collect all the multimodal data, all the EEG data, all the VR data, do extensive research at the same time, replay it, look at the camera, scene camera. So you can, if you wanted to do research, hardcore research, this could be a great solution. So there are a number of ways that people have been hacking at this. I don't think there is a single unified approach at the moment, and I doubt there would be, but there's lots of tools and solutions out there.
Awesome. Thank you. Next question. Does the wired system have better signal quality than the wireless system? So let's define what this wire is doing. I'm going to assume for a second that the wire you're talking about, is the cable that connects the headset to the computer. So no, there isn't a better quality when you do that. There's actually potentially worse quality in some cases. So in some cases, that cable can end up conducting current noise back into the proximity of the headset, which can show up in your system. So the wireless system, by being isolated, is a better solution. The one place where a wired solution
might be better is if you cannot transmit the data wirelessly. So in cases of in a conference hall or places where there are a large number of people or Wi-Fi interference, all these people with Bluetooth devices or many Wi-Fi routers transmitting data, very saturating the airwaves, you can start to get data loss and data packet drops. And that is problematic for Bluetooth devices such as the wearable sensing devices. The 5G systems are much more robust to that, but even they will have their limits. So in that regard, the wired system would be better. There are also some cases where you're not allowed to use a wireless system. In that case, a wired system would, of course, be more advantageous.
Awesome. Next question is, how are you, for the dry system, how are you able to handle large artifacts?
Magic. Excellent question. The large artifacts, as Cameron was showing you showed you with the video of Cameron doing the demonstration, those artifacts do get carried on the body. So you have a very large common mode artifacts on the body, which would typically saturate the amplifiers of the EEG. So you need to have a very large bandwidth amplifiers, which then reduces their resolution, or you have to have very high bits digitization so you can get the entire range. So in our approach, we're doing what's called a common mode follower. So we have one amplifier that acts as a reference for everybody. It has the very wide bandwidth and range, and it can receive all of these large inputs without getting saturated. We reference all the channels to that during data acquisition, and that allows us then to go in software when we re-reference the data, any common signals such as the common modes, 60 hertz, any common signals would get essentially algebraically removed. That is common process in EEG. That's not artifact removal. That's not algorithm approach. That's just looking at the difference between 2 points and the EEG. You are just by the nature of what you do, you look at the difference between these two. So anything that's common is gone. For that, you need good phase and gain matching, which we spend a diligent amount of effort to make sure in our systems.
Awesome. Next question is, what are the sizes for the EEG systems?
So the different systems have different sizes. The Neuracle systems have the caps in different sizes. The caps have electrodes sizes ranging from extra small to extra large. They go in 4 centimeter increments, which is standard for these kinds of elastomeric caps, so that they can stretch a little bit and still fit. The dry electrodes, they come in 2 sizes. Regular adult size and child size, and they have very wider ranges of fits, and we have mechanical moving pieces and adjustability to allow you to adjust these headsets so they're comfortable and they position the sensors reliably across this wide range of head sizes.
Awesome. Looks like the last question that we have right now is what kind of cleaning is needed for the EEG systems?
Okay, good question. So the Neuracle system has the cap needs to be cleaned. So you separate the amplifier from the cap. There's a very cool magnet that attaches the two together. There's a connector. You remove it. It makes the Apple connectors look like archaic. It has 64 connectors. It's really beautiful and clean. You separate the electronics from the cap. You can then take the cap and rinse it with warm water to get rid of all the gel, and then you put it to air dry. With the dry sensor system, since there is no gel, we include a power brush with each of our systems and an alcohol container, which you fill with 70% isopropyl alcohol. You dump the brush inside the alcohol container, and you're then able to clean each of the electrodes by applying the power brush onto the pins of the electrodes, and the power brush rotates very quickly, cleans them off with the 70% isopropyl alcohol. which dissolves the skin oils and fats that may be adhered to the electrodes, and at the same time does a mild disinfection. And then you leave it to air dry, and within a few minutes, the caps are dry and they're ready to reuse.
Awesome. Thank you for answering all those questions. It looks like those are all the questions that we have right now. We actually had just one other question come in. It was, so could we customize the electrodes of the, just in general customization, and then also customize the electrodes of the sleep headset?
So for first question, customize the electrodes, yes, for both the Neuracle systems and the wearable sensing systems, you can customize locations. Please talk to us, and we will happily explore what options, what locations you're looking for, and what solutions can be made for that. And then for the sleep band, that one is can also be customized, but it's a very different effort. So again, talk to us. We are in the business of trying to support your research, even in a one-to-one cases, but also hoping to develop applications that have a large-scale utility. So if your applications, have a large market, we're happy to start developing new headsets for those. So let us know what you need. This is below here is the email for us at Wearable Sensing, but if you email us there and you have any questions about the Neuracle high-density systems, we will be very happy to forward those emails to Xiaoshan and his team at Neuracle to answer your questions. And wherever you are around the world, we have a wide, we have distributors in over 40 countries right now. So let us know where you're calling from. If you'd like to talk to a local representative, we'll be happy to connect you.
Awesome. So it looks like those are all the questions that we have right now. If anyone has any last minute questions, feel free to send them in pretty much right now. Otherwise, thank you guys for all attending. Like Walid was saying, we're going to have an upcoming webinar here next month on biomarkers for stress with people in autism, and hopefully you guys can attend that upcoming webinar.
Thank you all for your time today. Thank you for your questions. Thank you for not making them too hard. And I look forward to seeing you in person once we start doing live meetings. But in the meantime, please join us at our next webinars. Thanks again.
All righty. Thank you, everyone.